Okay, so I sat down to write the key to the activity and decided to record myself doing it. I will post the key, but I figured maybe or hopefully you can find this video helpful, okay? So let me start by saying this is the key. Okay, so the first problem, I have to find the derivative of a sum, and we know the power rule, right? We know that the power rule, let me remind you real quick, the power rule goes, if I take the derivative with respect to x of x to the n, I bring the exponent to the front, keep the variable, subtract 1 from the exponent. That's it. So I'm going to do this term by term. Now, this notation means I'm going to take the derivative of this function with respect to x. Once you apply the rules, you drop the notation. So this is equal to, and this would be 3 times 8. So you do 3 times 8, you get 24x. And then the rule tells you to subtract 1. So 3 minus 1, you get 2. The derivative of x is just 1. So you can think about it like there's a 1 here. So if I bring the 1 to the front and subtract 1, I get 1 minus 1, which is 0. So it's just the coefficient. Or you can think about it like it is the slope of the line. So that's a 1. And then the derivative of a constant, it's equal to 0. So you don't have to write that 0. So if you just leave it like this, that'll be perfect. Okay. Now for the second problem, the first thing I'm going to do is I have to rewrite y so that it makes sense and I can apply the power rule. So let me remind you one more time that if you have the mth root of x to the n, this is the same as x to the n over m. So the exponent goes on top, and then this tells you what root you're taking, okay? And then let me also remind you, which I know you know, but if you have 1x to the n, this is the same as x to the negative n, okay? So this is now y, it's equal to x to the 1/3 minus x to the negative 3. I'm keeping the y because I have not done any calculus yet. I'm just rewriting my function. Now I take the derivative and I get that dy dx is equal to, you bring the exponent to the front, I get 1/3 x to the 1/3 minus 1, and then negative 3 times negative, you get plus 3x to the negative 3 minus 1. And you can feel free to skip this step, okay? I'm doing it so that you see where things come from. So the way I do this is if I have to subtract 1 from a fraction, I think about 1 like, in this case, 3 divided by 3 because it is the common denominator. So this would be negative 2/3. Oh, so then the final answer will be 1/3 x to the negative 2/3 plus 3x to the negative 4, okay? Not too bad. Okay. Now for C, I see a fraction. The moment I see a fraction, I know that I have to use the quotient rule, right? And the quotient rule goes, if I have the derivative with respect to x of f divided by g, bottom, derivative of top minus top, derivative of bottom over bottom squared. Or low d high minus high d low. Draw a line and square the low, All right. And then also the derivative of e to the x is itself, unless I replace x with a function. When the time comes, I'll review that. But if I have here a function instead of x, I would have to multiply by the derivative of that function, right? So if I had a function, I have to replace x with the function and then multiply by the derivative. I'll remind you in a minute. Let me apply it here first. So s prime of t, it's equal to bottom, derivative of top minus top, derivative of bottom divided by bottom squared. And I know I've said this a lot, but I'm going to say it again. You can skip this step if you feel comfortable skipping the step. This is going to be 1 plus t squared. Derivative of e to the t is e to the t minus e to the t. Derivative of 1 plus t squared. Well, the derivative of 1 is equal to 0, so that goes away. Derivative of t squared is 2t. Bottom square. 1 plus t squared. Squared. No need to simplify. And, oh God, what is going on? No need to simplify. Let me mention something real quick. Be careful with the parentheses, okay? I see a lot of students write 1 plus t squared times et. And I know what you mean, but it is mathematically incorrect. If you write 1 plus t squared times e to the t, you're multiplying these two together and then adding 1, and that's not what we want. So be careful, okay? All right, let's get into more interesting problems. So again, let me remind you, if I had x squared times x cubed, the whole thing raised to the 1/2, then you would do x squared to the 1/2 times x cubed to the 1/2. That's not the case here. If you have a sum, you don't get to distribute the exponent, okay? This is an exponent. So you have to use algebra first. So this is dx x squared plus x cubed to the 1/2, and you have to use the chain rule, okay? One more time, notice that I'm just using algebra from here to here, so I keep the symbol. Once I apply the rules, then I get to get rid of the symbol, okay? So let me remind you of the chain rule. Once you get the chain rule, everything else, it's so simple. So the chain rule is used when you have a composition of functions. So say you have f of, and then g of x is your inner function. So this is g of x. You want to take the derivative of this whole thing. This will be equal to, you take the derivative of the outer function, so f prime. You replace your variable with the whole function g of x, what I keep calling the baby function. And then you have to come back and multiply by the derivative of that baby function, okay? So this is sort of like saying if I'm taking the derivative of f with respect to x, I'm sort of taking the derivative of f with respect to g, and then the derivative of g with respect to x, okay? That's what's actually happening. So I'm going to do it. Now, again, once you do this enough times, there's no need for you to write all these steps, but I'm going to do it this one time just to remind you what's happening, right? So if this is, since I have x squared plus x cubed to the 1/2, then this would be the inner function, g of x, and then f of x will be equal to x to the 1/2, right? Because if you do f of g of x, you replace x with g of x, and then you'll get that since g of x is x squared plus x cubed, you end up having what you had to begin with, okay? So f of x is equal to x to the 1/2, then g of x is equal to x squared plus x cubed. So f prime of x is equal to 1/2 x to the negative 1/2. G prime of x is equal to 2x plus 3x squared. And I'm ready to put my derivative together. So let me make this a little smaller. So resize. I'm making this a little smaller down here. So according to the formula, I need the derivative of f evaluated at g. So I take the derivative of f and I replace x with g. So I have that the derivative of this, it's equal to, so I had 1/2, replace x with g of x. So replace x with g of x. So I get x squared plus x cubed. And then don't forget the exponent, so negative 1/2. And then multiply by the derivative of g, which is 2x plus 3x squared. So 2x plus 3x squared. See how I am very careful with my parentheses, okay? Hold on, I feel like I don't like the colors here. So this should be blue. This should be blue. And this should be black. Is that what I'm doing? Yes. This should be black. And then this should be blue. And now everything will make sense now that I have the correct colors. Okay. Now, if you think about it, what's happening is, that's what I mentioned in class yesterday, actually. I mentioned that it is so common to have that the outer function is a power, right? That we think about it like, oh, what if I want to take the derivative of a function raised to a power? This would be, you bring the exponent to the front ignore the baby function, right? Subtract 1, so I'm taking the derivative of the outer function. And then you come back and multiply by the derivative of the baby function, okay? All right, so again, if this is my baby function g of x, this would be the derivative of it. Perfect. Okay. So maybe make this smaller too. Resize, very, very small. Like I don't want you to memorize that. I just want you to see that the outer function is a power. Okay. Now, E. So if you look at it, like if you zoom in, I see I'm multiplying two functions, right? Since I'm multiplying two functions, I have to use the product rule. So let me remind you of what the product rule says, okay? So the product rule, the product rule goes, I'm going to find the derivative of f times g. I do second one derivative of the first one plus the first one derivative of the second one. The order doesn't really matter here because you are multiplying and adding, but I like to stick to this order because it's the same I use for the quotient rule, okay? All right. So let me set it up. This would be a second one, e to a negative 2x, times the derivative of the first one plus the first one times the derivative of the second one, okay? That's it. So let's just do it. This would be second one, e to a negative 2x, derivative of x is 1 plus x times the derivative of e to a negative 2x. And that's what I was saying, right? And you don't get to forget this. The derivative with respect to x of e to the x is itself, okay? But if I replace that x, if I replace x with a function of x, then it turns into a chain rule problem, okay? It turns into a chain rule problem. So you can either do it with the f and g's, or you can just think about it in general. So let me maybe do it with f and g, okay? So I'm going to do this derivative here, okay? So let's say if I want to find the derivative with respect to x of e to a negative 2x, and I want to write this e to the negative 2x, I want to write it as f of g of x, then my outer function f is e to the x, my inner function g will be equal to negative 2x, okay? Now, the formula is not going to change, right? The formula goes, you take the derivative of the outer, which in this case tells me that f prime is equal to e to the x. You replace the x with your function g, and then you come back and multiply by the derivative of g, which in this case is negative 2, okay? So one more time, if I want to do this using the notation, then this would be the derivative of e to a negative 2x will be equal to f prime of g of x times the derivative of g, okay? So let me just go back to pink for no reason. So this would be g of x times the derivative of g of x. So long story short, I get that f prime is itself evaluated at g of x, so I replace x with negative 2x, so that's how I end up with e to the negative 2x, which is the inner function, and then you come back and you multiply by g prime of x, which is negative 2. Negative 2. So long story short, I mean, I hope you see the pattern, right? So what's actually happening is when you apply the rule, you can think about it in general. So in general, what's happening is you want the derivative of e to a function, not a problem. Derivative of the outer, replace x with the inner, come back and multiply by the derivative of the inner. And the inner function in this case is just the exponent of e to the x, okay? I hope that makes sense. It does. I know it does. Okay. So let me make it smaller. There's a lot of pink here. Maybe let me make it, I don't know, maybe let me make it black. Okay. Let me highlight it. I'm just bored of the same colors. Okay. Look at that beauty. So all this, I said a lot of words. So long story short, the derivative will be, maybe just copy paste it because I did all this work for a reason. So copy and then hopefully paste. Paste. There you go. That's it. That's the answer. You don't have to simplify it. You don't have to do anything. You can even skip writing that one if you want to. Okay. F. Okay. So, I don't know why I decided to use secant. The problem with secant is that the derivative with respect to x of secant of x, it's equal to secant of x tangent of x. So when you have a composition of function, when you replace theta with 2 theta, now it turns into the chain rule, but it'll look ugly because the derivative of secant 2 theta will be secant 2 theta tangent 2 theta times the derivative of the baby, which is 2. But let me just do it. Okay. I'm going to set it up. So what do I see? I see a function raised to the 10th power. So I know, using my chain rule first, I know that this is going to be, I bring the exponent to the front, ignore the baby function, subtract 1, multiply by the derivative of the baby function. That baby function happens to be theta squared times secant of 2 theta. So I need to multiply by the derivative of theta squared times secant of 2 theta. Oh, now, to find this derivative, I have a product, not a problem. I have to use the product rule. So this is going to be equal to, and then again, there are a lot of these steps that you can skip if you feel comfortable skipping them. So this, I copy down here, and now if this, okay, and now you have to use the product rule for this. So first we'll use the chain rule. Now I'm going to use the product rule, okay? So this is going to be the second one like it is. So second one like it is. So secant of 2 theta times the derivative of the first one, which we know how to do, right? We know how to take the derivative of theta squared and then plus. And now you leave the first one alone. So back to pink, theta squared, and then you need the derivative of secant of 2 theta. Okay? So, pop. Okay. So what does that mean? It means that my next step would be everything stays the same. Everything is the same. Copy, paste, paste. Sometimes it's just, now you see what I see when I keep saying paste. Oh, there it is. Paste. So I'm going to go here, find the derivative of theta squared. Theta squared. You get 2 theta. And I have to replace secant 2 theta with the derivative of secant 2 theta with the derivative of secant 2 theta. So let me do it here. So I'm going to do it here. The derivative with respect to x, or I mean, let me use theta. Theta of secant theta, it's equal to secant theta times tangent theta. Not a problem. But one more time, if I replace theta with a function, then it turns into a chain rule. So I take the derivative of secant, replace the thetas with the function, come back and multiply by the derivative of the function. So what I'm saying is, if I now, instead of having theta, I replace theta with a function of theta, let me put it in parentheses so that it's like very dramatic, 2 theta, then I have to go to the derivative of the outer function, replace each of the thetas with the inner function, which again, it's 2 theta in this case. So you get 2 theta and then 2 theta, and then come back and multiply by the derivative of the baby function, which in this case is just 2. So all this work to get that the derivative of secant of 2 theta is secant of 2 theta tangent of 2 theta times 2. That's it. We are done with this derivative. Let me highlight. I feel like this deserves some highlighting. Look at that beauty. Okay, and then I have one more problem, which is sine of cosine of tangent, okay? I want to find the derivative of sine of cosine of tangent. Again, I look at it from like 200 feet away, and I see sine of something. So I take the derivative of sine, I get cosine ignore the baby function, so I leave it, I replace x with the baby function, and then I come back and multiply by the derivative of it. So f prime of x is equal to cosine, ignore the baby function, come back and multiply by the derivative of that baby function. Well, that baby function, it's cosine of tangent. It's cosine of tangent, so it requires you to use the chain rule again, okay? Not a problem, we know how to apply it, so chain rule. And then I have to multiply by the derivative of cosine of tangent of x. Okay. So now I'm still completing the derivative, so I can put an equal sign there. Let me copy this whole thing. Copy, paste, paste, copy, paste. Now the derivative of cosine tangent, well, I look at it, I see a function, right? I see tangent inside cosine, I use the chain rule. Derivative of cosine, leave tangent alone, come back and multiply by the derivative of tangent. Derivative of tangent is secant squared. Derivative of cosine, it's negative sine. So this is negative sine, leave the inner function alone, come back and multiply by the derivative of the baby function. That baby function is tangent of x. Okay? I have one more. I still have to find the derivative of tangent of x. Not a problem. I copy everything again. So copy, paste. Copy, paste. There it is. Derivative of tangent of x, secant squared. Oh, let me use blue. Yeah. I don't know. I don't know. Should it be pink? Yeah. Secant square of x. So the last thing I want to do is, let me remind you of the derivatives of the trig functions. So one more time, if you have cosine of x, the derivative of cosine is negative sine of x. The derivative of sine of x, it's equal to cosine of x. The derivative of tangent of x, it's equal to secant square of x. And you can prove this easily by thinking of tangent of x. Oh my God, I cannot write. Tangent of x as sine of x divided by cosine of x, and then use the quotient rule, right? Because you know that the derivative of tangent of x will be equal to the derivative of sine of x over cosine of x. And then you can use the quotient rule and simplify, and you get your answer. And then the derivative of secant of x, it's equal to secant of x tangent of x. This is a very common function, so you can also prove this by using the fact that secant of x, it's equal to 1 over cosine of x. And then the derivative, right? The derivative of secant of x, you can even use the chain rule by thinking of cosine of x to the negative 1 and then using the chain rule, or you can use the quotient rule. Okay, I think that's it. I hope this helps, okay? Let me know if you have any questions. Bye-bye.